Welcome dear students for the grade 13 chemistry class of St. Peter's College, Colombo for Nigabu branch. In this video, we are going to discuss about the volumetric titrations. Why we do volumetric titrations? Normally we do volumetric titrations to determine the concentration of a solution by using another solution of known concentration. And in this, usually we measure the volumes of the solutions. For that, we use two solutions. One which we know the concentration and the other one which we have to determine the concentration. And we measure the volume of the solution that completely react with the other solution. And then we can calculate, if we know the stoichiometry of the reaction, we can calculate the concentration of the unknown solution. So this is the procedure which we follow when we do a volumetric titration. And this is the setup we make in the lab when we do a titration. To that we need pipette, titration flask and the pipette stand. And for titration we use two solutions, as I told you. In here we should add the pipette which we know the concentration, and we call that titrant. And the solution which we have to find the concentration, we should add to the titration flask, and it is called analyte. Then the volume of the titrant required to reach this stoichiometric mixture we call equivalence point volume. So when we do a titration, we have to measure the volume of the titrant. In a titration, there are two important points. First one is equivalence point and the second one is end point. There are 2 points. Equivalence point means, which I told you before, the stoichiometrically, when the titrant totally react with the analyte, at that point the volume which we add to the analyte, we call at that point we call the equivalence point. But the end point is the point where we stop adding titrant to the analyte. So there are 2 points, because we cannot find the equivalence point. Always the end point is excess than the equivalence point. So how we find this end point? For that, we have to use another substance. We call that indicators. We have to add a small amount of indicator to the analyte before we start the titration. And at the end point, this indicator change its color, because always indicators change their colors with the change of pH. So, as I told you, there are 2 points, end point and equivalence point. So, it is difficult to catch the equivalence point, but we can find the end point. And there is a difference in volumes between equivalence point and end point. Sometimes it can be a one drop, but there is a difference. So, for that difference, we call titration error. And if we construct a curve, volumetric titrant against pH, it is like this. You can see here, this is the equivalence point of our titration and this is the end point. In green color arrow shows the end point and red color arrow shows the equivalence point. You can see here there is a very small difference between these two volumes, but it makes a significant pH change here. This is a very small value, but it makes here significant difference in pH. In this lesson, we are going to discuss about 4 types of titrations. First one, strong acid, strong base titration. Second one, weak acid, strong base titration. And third one, strong acid, weak base titration. And fourth one, weak acid, weak base titrations. To study about these titration, here we are going to construct titration curves. And for this we use 2 solutions of acid and base which we know the concentrations, because in here we are going to construct the curves in theoretically. So for that we use both acid and the bases which we use to construct these curves with the known concentrations. And by using these acids and bases of known concentrations, we can construct the titration curves. Now, let's consider about these titration curves. First, let's take the strong acid, strong base titration. Here you can see that this is the curve. Volume of the titrant in x-axis, it shows the volume of the titrant base, and as analyte we have taken here acid. Here you can see we have added base to acid, and gradually the pH change because the titration flask contains here acid, and when we add titrant base to that, the pH change, and we can find a steep pH change like this, and the middle point of that steep change is called the equivalence point. So in strong acid, strong base titration, the equivalence point is pH 7. If you see carefully this graph, you can find that. So then in this graph, we are going to check if we use the or if we change the concentrations of acid and base, what happened to this pH curve? What are the differences? When we see this graph, you can see there, when the strength of acid become weaker, here 2, 3, and here pH 1, pH 2, pH 3. If we use a more weaker acid, what happened to the titration curve? It is like this. And when we compare this curve carefully, we can find the spread of pH value decrease. I can show you that when we use the 1N HCl and 1N NaOH. Here, this is the curve, and steep change of pH lies on this area. But if you take 2N more weaker acid, like this in green color, and weaker base, you can see this distance is shorter than the first one. The red color distance shorter than the black color distance. That means when we use initial concentrations in lower values, the spread of pH curve decrease. This is the spread of pH curve. You can see it decrease. Now let's take another titration. Weak acid, strong base titrations. In here, you can see acid is in titration plus, because here we can see the value of pH is 2.1, 2.5. So that means the acid is in titration plus and we have base on the burette. And pH change like this, and there's a steep change of pH we can find in this area, and this is the equivalence point. It lies between 8 and 9 pH values. This is the equivalence point of this titration. And there's a special thing we can find. There's a buffer region. This is the buffer region of this titration, because in this region we cannot find a steep change of pH. When we add base, the pH value not change in higher values. Normally we call this area buffer region. In our next lessons we are going to study more about the buffer regions. But you should know, in weak acid strong base titration, buffer region lies below the equivalence point. This is the equivalence point. You can see here, buffer region lies below the equivalence point. And in here also we can check when we change the initial concentrations of weak acid. What happened to this steep change of pH? Let's check that. In here, I have shown you the Ka value of the weak acid which we take here. First one, 10 to the power minus 2, 4, 6 and 8. And here you can see, when we change the concentrations of the base, this pH shifts more to basic size. This steep change of the pH value shifts more to this side, to the basic side. Because when the weaker the acid, when we use weaker acid, this equivalence point, in this one equivalence point here, and the second one, it shifts more to the basic size. So you have to check about this weaker acids Ka value and the equivalence point changing directions. Now let's take the next one, strong acid weak base titrations. In here we have add HCl to the base. In this graph you can see that the base is in titration class and we have add HCl to the base. Equivalence point is lies between 4 and 5 pH. So in here also we can find the buffer region because we use here weak base, but the buffer region lies above this is the equivalence point, and buffer region you can see here lies above the equivalence point. And if we check the acidic strength of the weak base which we use, when we use the weaker the base, the equivalence point shifts more to the acidic side. Weaker the base, here you can see, weaker the base, the equivalence point shifts more to the acidic side. So there's a difference when we use weak base and when we use weak acid. The equivalence point shifts in different ways. Now let's take the weak acid weak base titration. So it is like this. Here we use here acetic acid and ammonia. Acetic acid is a weak acid and also ammonia is a weak base. And if we construct a pH curve, it is like this. You can see there is no steep pH change in this graph. So it is very difficult to find this equivalence point. Normally we cannot easily find an indicator to detect this equivalence point. Now this is the summary of 4 types. Strong acid, strong base, weak acid, strong base, strong acid, weak base and weak acid, weak base. All titration curves are shown in one graph. So you can compare these graphs and understand them by using this summary of 4 types of graphs. Now we have to discuss about the polybasic and polybasic acids and polyacidic bases. I can give you as examples. If we take oxalic acid, sulfuric acid, phosphoric acid, all these acids are polybasic acids because these acids have more than one ionizable proton per molecule. If we take sulfuric acid, it can produce 2 H plus ions. So that's why we call them polybasic acids. So likewise, if we take carbonate, sulfate and phosphate anion containing bases, these anions can accept more than one OH minus ions. So we call them polyacidic bases. So I have shown you here the reaction of dibasic acid H2A is here represented as the dibasic acid, and it dissociates like this. It can give 2 H plus ions. That's why we call it dibasic acids. And here diacidic base, you can see here carbonate, sulfate and phosphate can accept more than 1 H plus ions, so we call it diacidic base. Now let's take polyacidic base titration. For that, here we are going to construct a titration curve, and we use sodium carbonate and HCl for our titration, and HCl as titrant. Then if we construct a curve, it is like this. We can see here there are 2 rapid change in pH in here and here. There are 2 rapid change in pH values. Now let's see why we can find these two different steep change in pH. Because in here we use sodium carbonate and HCl, and sodium carbonate is a strong base or strong electrolyte, and it fully dissociates in solutions like this: sodium plus aqueous ion and carbonate minus 2 aqueous ion. It fully dissociates. And the major contents in the mixture in the initial point are sodium plus aqueous ions, carbonate minus 2 ions, and H plus ions, Cl minus ions, and water. So, first the H plus ions from HCl react with the carbonate ion and form the HCO3 minus or bicarbonate minus ion. This is the first reaction that occurs in the solution. And in the second reaction, the protons which we add to the solution react with this form bicarbonate ions and form the carbonic acid. And in the first part of the graph, sodium carbonate react with acid and produce the sodium hydrogen carbonate. According to this reaction, you can see that in the first part of the graph, sodium carbonate react with HCl and form sodium chloride and sodium bicarbonate. And at that point, the mixture contains, end of this reaction, the mixture contains sodium plus aqueous ion, chloride minus aqueous ion, and bicarbonate ions that dissociate from sodium bicarbonate. And at the first equivalence point, this equilibrium exists in the mixture. That means the bicarbonate ion dissociates partially to carbonic acid and hydroxyl ion. So at the first equivalence point, this equilibrium exists in the solution because only sodium bicarbonate is formed in the solution. In the second part, the sodium carbonate the sodium bicarbonate further react with HCl and form the sodium chloride, carbon dioxide, and water. Now, I think you can understand in the first part of the reactions, there's no carbon dioxide is formed. But in the second part of the reaction, we can find the carbon dioxide. So, sodium bicarbonate further react with HCl and form the sodium chloride, carbon dioxide, and water. And let's see what is the equilibrium that exists in that point. At the second equivalence point, This is the equilibrium exists in the solution. Because at that time carbonic acid and water dissociate and form the HCO3 minus ion and H3O plus equals ion. So this is the equilibrium exists in the after the second equivalence point of the solution. So that's why we can find two changes, two equivalence points in our graph. This is the end of our lesson, and in our next video I hope to discuss